Morning everyone, thank you for joining us for this GCSE Chemistry live group tutorial. Today's topic is limiting reactants and percentage yield. So welcome back to those of you that have been joining us over the past few weeks for our chemistry sessions and for our other subject sessions as well. Welcome, I can see there are a few new people today. Just to give you an idea of what this session will look like, this will run for 1 hour, so we'll end around 11:15. And as usual, our tutor will go through some content, go over some exam questions, which should be really helpful. And then at the end, we'll have time for any questions from you guys. So put any questions in the Q&A and chat box. I'm Tilly, I work at my tutor, so if you have any questions for me, let me know. And our tutor today is Aman, who lots of you know already. Aman studies medicine at King's College London and has completed over 150 lessons with us at my tutor. So someone's just asked, can you make some Spanish lessons? We are planning what our language lessons will look like, so I'll update you as and when I can about what languages we'll be adding to our online school. And someone's just asked, Armin, is this for the AQA syllabus?
So I aim to cover most of the curricula. So today we'll be covering things on the AQA and EdXL syllabus. Percentage yield and limiting reactants are both in the AQA syllabus and in the EdXL syllabus and OCR syllabus. So all the curricula have these topics. And if you look at the webinar that I covered on Monday, which is kind of the foundations to this topic, again, all of the stuff that we covered, apart from empirical formulae, was in all the curricula.
Brilliant, thank you. And as Aman mentioned, you can watch back our previous tutorials, so those are accessible on the My Tutor YouTube channel. And we've also got some shorter topic videos that go through some exam questions, so if you want to check those out after the tutorial, please feel free to do that. Cool, then let's kick off.
Yeah, just before we start, if everyone could grab a calculator, that would be really useful, just because like Monday's session, we'll be doing a lot of exam questions kind of within the content that I'll be doing today. So if you could get some calculators, that would be really helpful, just because they're all calculation type questions in this topic. So we'll be starting with a bit of a recap of what we covered last on Monday. So we did our main equation on Monday. First of all, we started by calculating the relative atomic mass and the relative formula mass. And then we used those to then calculate our moles, which is equal to our mass over our relative formula mass or relative atomic mass. So I'll put AR there. So we'll be using those equations today throughout, and they're really important. So as I said, Monday's session was basically a foundation session to all of the things that we'll be covering this week. So if we have a look at our first question then, a compound was analysed and found to contain 9.8 grams of nitrogen, 0.7 grams of hydrogen and 33.6 grams of oxygen. What is the empirical formula of the compound? So hopefully you remember that empirical formula means the simplest ratio. So the example I gave on Monday was carbon dioxide is CO2. So the simplest ratio of those elements is 1 carbon and 2 oxygens. It wouldn't be C2O4 because that's not the simplest ratio. The simplest ratio is CO2. And the empirical formula is aiming to find that simplest ratio. And we can use the masses of elements to help us by calculating the moles of each element. So if we know that our equation is the moles equals the mass over the AR, then we know then that if nitrogen has a mass of 9.8 grams, the moles will be 9.8 divided by 14. So if anyone's got a calculator, if you could tell me what the number of moles is then, 9.8 divided by 14, sorry, so that's nitrogen. Hydrogen will be 0.7 divided by 1, and oxygen will be 33.6 divided by 16. And I remember saying when we were doing empirical formulae on Monday, you always only count it as 1. So excellent. So people are saying the number of moles for nitrogen is 0.7. Great. Okay. So what's the number of moles for hydrogen then? We don't need to use a calculator to do that. It's just 0.7 divided by 1. So it's just 0.7. And then oxygen, 33.6 divided by 16. What's the number of moles for oxygen? Excellent, 2.1. Okay, so now we have the number of moles of all three elements, and we can just find the ratio then. So remember, in ratios, we always divide by the smallest number. So 0.7 is the smallest number. So if we do 0.7 divided by 0.7, we get 1. 0.7 divided by 0.7, we get 1. 2.1 divided by 0.7, we get 3. So that means the simplest ratio of these elements is 1 to 1 to 3, and therefore the empirical formula is HNO3. So it's nitric acid, HNO3. Does that make sense what we covered there? Does anyone have any questions about empirical formulae? If you want to do more questions, if you go back to Monday's session, we did quite a few questions on empirical formulae. But before we move on to the next question, does anyone have any questions on empirical formulae? Well done to everyone sending me in answers. You're exactly correct. Okay. So let's go on to the second question then. We want to calculate the maximum mass of sodium carbonate that could be formed by reacting 14.5 grams of sodium chloride with calcium carbonate. So we have a look at our reaction. We've got sodium chloride reacting with calcium carbonate, forming sodium carbonate and calcium chloride. So we want 14.5 grams of sodium chloride is reacting, and we want to know the maximum mass of sodium carbonate. So just like we just did in the previous question, we need to know the number of moles of sodium chloride, and then we can use the balanced equation to work out how many moles of sodium carbonate there are. And if you remember, our equation is moles equals mass over the AR. That means then if we have the moles of sodium carbonate, we can use the AR and the moles to calculate the mass, which is what this question is asking. So to calculate the moles of sodium chloride, does anyone remember what we need to do? Or what's the equation or the numbers that we need to input into our equation to work out the number of moles of sodium chloride? So we're going to be using the reaction here, moles equals mass over AR. So the number of moles then will be the mass, which is 14.5 grams, divided by the AR. And remember, the AR is all the elements added up. So it's their relative atomic masses added up to form the relative molecular mass, which is MR. So the reason this says AR is these are the relative atomic masses of each of the individual elements. But if we're thinking about a formula, we do the MR, which is the relative formula mass or molecular mass. So sodium chloride has a relative formula mass of 23 plus 35.5, which is 58.5. So the number of moles of sodium chloride is 14.5 divided by 58.5. So what's that then? On a calculator, 14.5 divided by 58.5. How many moles is that? And then once we've got the answer to that, we need to look at our reaction. And if we look at our equation here, we can see that there are 2 moles of sodium chloride. Excellent, everyone's telling me 0.25, really great. So that is correct, so that's 0.25 here. So 0.25 moles of sodium chloride. So if we look at our balanced equation, that means that there are 2 sodium chlorides reacting to form 1 sodium carbonate. So if the number of moles of sodium chloride is 0.25, that means as a proportion, 0.25 moles of sodium chloride are reacting, but we only form 1 sodium carbonate. So we need to divide the number of moles by 2 because the ratio is 1 to 2. So if 0.25 is 2 to 1. So if 0.25 is 2, we need to divide by 2 to get 0.125. So 0.125 is therefore what 1 mole is. And then to calculate the mass of sodium carbonate, all we need to do is rearrange our equation, which is moles equals mass over MR, to say that the mass equals the number of moles multiplied by the MR. And the number of moles we've said is 0.125. And the MR of sodium carbonate will be 23 times 2, which is 46, plus 12, which is 58, plus 3 times 16, which is 48, which gives us 106. So 0.125 times 106, what does that give us then as a final mass of sodium carbonate? Someone's saying 13.25. Great, everyone's saying 13.25. Yep, that's the answer then. So there are 13.25 grams. Remember, we always give to 3 significant figures, so it would be 13.3 grams. Okay, well done, everyone. Excellent. Okay, so that's a recap of what we covered last week, and it's really important that we're happy with kind of those questions, because today we're going to be building on those. So last week, on Monday, we looked at moles equals mass over MR. We looked at forming empirical formulae, but there's one final part then, and that is forming a balanced equation from a mass. So we've looked at forming an empirical formulae from masses, but we haven't looked at actually forming a balanced equation from masses. And this is in all the syllabuses again. So we have calculated masses from equations and used masses to produce an empirical formula. The final type of question is balanced equations from the masses. So we can work out the ratio of moles of each reactant and product in order to write out a balanced equation. So as an example, we've got potassium nitrate. It decomposes on heating to give potassium nitrite and oxygen. When 4.05 grams of potassium nitrate is heated, 3.4 grams of potassium nitrite is produced. Use this information to construct a balanced chemical equation for this reaction. Now I'm going to go through this slowly because there's lots of different parts going on. So the first thing is we can see that we're going to have some kind of reaction which is KNO3, which is our potassium nitrate. It's going to decompose to produce KNO2 plus oxygen. And effectively, to form our balanced equation, we need to know which numbers go in front. Now, you may be thinking, oh, but can't we just balance it how we normally do? You can, but in this exam question, they're not looking for that. They're looking for your use of moles equals mass over the MR and that equation, and knowing then how to use the moles to work out the balanced equation. But we can definitely use the checking method afterwards once we've formed our balanced equation. So first of all, we can see that we've got the mass of potassium nitrate, got 4.05 grams, and we've got the mass of potassium nitrite, 3.4 grams, but we don't have the mass of oxygen. Now, hopefully you remember from last week that the mass of reactants is always equal to the mass of products. So if we have a look at our reactant, it's only potassium nitrate, which is 4.05. Our potassium nitrite is 3.40. So that means our oxygen is 4.05 minus 3.4, because the mass of the reactant is always going to be equal to the mass of the products. So 4.05 minus 3.4 is 0.65. So that's our grams of oxygen. So now that we've got the grams of all of the reactants and the products, we can start by calculating the moles. So remember, the moles equals the mass over the MR or AR. So in potassium nitrate, that is 4.05 divided by the MR or AR. So in this case, it would be MR. So potassium has an AR of 39. We add that to 14, which gives us 54. And then we add that to 48, which is 16 times 3. So then we get a total MR. So what's the total MR of potassium nitrate? So 39 plus 14 plus 48. That's the total MR. Excellent, 101. Okay, great. So that is 101. Well done, everyone. And then if we do potassium nitrite, so again, this is 39 plus 14, but plus 32. So what's 39 plus 14 plus 32? So what's the MR of potassium nitrite? Excellent, 85. Great. And then oxygen is O2. So that means it is 16 times 2, which is just 32. Okay, so now we can calculate the moles. So the moles of potassium nitrate will be 4.05 divided by 101. So what's 4.05 divided by 101? So moles equals mass over the MR. So 0.04. Okay, great. So the number of moles of potassium nitrate is 0.04. What about the number of moles of potassium nitrite? So that will be 3.4 divided by 85. Okay, 0.04 again. Great, well done. Final one, oxygen, 0.65 divided by 32. So what's 0.65 divided by 32? 0.02. Okay, excellent. So hopefully you can see they're quite nice numbers. And again, we just need to work out the simplest ratio. So 0.02 is the smallest number. So we divide by 0.02. So 0.02 divided by 0.02 is 1. 0.04 divided by 0.02 is 2. And 0.04 divided by 0.02 is 2. So that means our reaction is 2 potassium nitrates, which decomposes to form 2 potassium nitrites plus 1 oxygen. And then if we have a look at first our potassiums, we've got 2 potassium on the reactant side, 2 potassium on the product side, 2 nitrogens, 6 oxygens, 4 plus 2, 6. So that's definitely balanced. So that's our checking mechanism at the end. So that's the final type of equation or question that you might be asked using the moles equals mass over the formula mass, or we want to find a balanced equation from the masses. Does anyone have any questions about those? If not, we'll do another 1 or 2 questions on these. Okay. So nitrogen reacts with hydrogen to produce ammonia. So again, if they've given you in brackets what the reactants and products are, try and write out a balanced equation. Sorry, you don't need to write out a balanced equation, but just try and write out a equation. So nitrogen plus hydrogen goes to NH3. So again, that's not balanced, but we don't need to balance it. We're going to use the masses to help us. So when 2.1 kilograms of nitrogen is reacted with hydrogen, 2.55 kilograms of ammonia is produced. So what's the mass of hydrogen? So 2.1 kilograms of nitrogen is reacted with hydrogen and it produces 2.55 kilograms of ammonia. What's the mass of hydrogen? Okay, someone's saying 0.45 kilograms. Excellent, well done. And that is because, remember, the masses of the reactants equals the mass of the product here. So if 2.55 is the amount of product formed, then that means our reactants need to add up to 2.55. Well done, everyone. Okay, the next thing to notice is that we're in kilograms. Remember then that the equation moles equals mass over the MR. We always use the mass in grams, so we need to convert these to grams. And remember, there are 1,000 grams in a kilogram. So to convert to grams, this would be 2,100. This would be 450, and this would be 2,550. Okay, so moles equals mass over the MR. We now have all the masses, and now we can calculate the MR or the AR. So in nitrogen, it's N2, so it's 14 times 2, which is 28. Hydrogen is H2, so it's 1 times 2, which is 2. And NH3 is 14, which is nitrogen, plus 3, which is 17. So now we've got the masses and we've got the ARs or MRs. So the next thing to do is calculate the moles. So for nitrogen, if we do 2,100 divided by 28, what do we get? 2,100 is the mass divided by the AR of 28. What do we get? Excellent, 75. Well done. Okay, what about hydrogen? So we do 450 divided by 2. So that's 225. And the final one is 2,550 divided by 17. So what's 2,550 divided by 17? Excellent, 150. Well done. Okay, so again, let's see our ratio. The smallest number is 75. So that means nitrogen is 1. 225 divided by 75 is 3, and 150 divided by 75 is 2. So we've got our ratio there. So that means nitrogen is 1. There'll be 3 hydrogens forming 2 ammonias, and we can check that. There are 2 nitrogens on the reactant side, 2 on the product side, 6 hydrogens, and 2 times 3, 6 hydrogens on the product side. So that is a fully balanced equation. Well done to everyone that gave me answers. We'll do one more of those questions. Not sure why that's been cut off, but anyway. Ethane reacts with oxygen to produce carbon dioxide and water. When 8.10 grams of ethane is reacted with oxygen, 23.76 grams of carbon dioxide and 14.58 grams of water are produced. So first of all, let's try and write this reaction. So we've got C2H6, ethane. It reacts with oxygen, and it's going to produce carbon dioxide and water. Okay. We have 8.10 grams of ethane reacting with oxygen, so we don't know our mass of oxygen yet. We know there are 23.76 grams of carbon dioxide, and we know that there are 14.58 grams of water. So what's the mass of oxygen? So remember, the mass of the reactants equals the mass of the products, so what's the mass of oxygen then? Someone's just asking me, if you only work out the answer of the equation, how many marks can you get? You can probably only get 1. So in a lot of the mark schemes, they won't give you marks for just getting the equation. You have to be able to work out using the moles and the masses. So this question is saying using the information provided. Excellent, so 30.24, well done. That's grams of oxygen. Okay, so what about the ARs? So I'll tell you that the AR of carbon is 12, the AR of hydrogen is 1, the AR of oxygen is 16. So for ethane, it is C2, so 12 times 2, which is 24, plus 6, which is 30. Oxygen is O2, so that's 32. CO2 is 12 plus 32, which is 44. And H2O is 2 plus 16, which is 18. So we have our masses and we have our ARs. So the next thing to do, someone's asking me, how do you work it out? What are you wondering what we can work out? If you're talking about the mass of oxygen, it's because the mass of the reactants is equal to the mass of the products. So if we know the mass of the products is 23.76 and 14.58, if we add those together, we get the total mass of the products. We then subtract 8.10 and we should be left with what the mass of the final reactant is. Okay, great. So let's work out the number of moles then. So the moles is equal to the mass over the MR. So for ethane, 8.10 divided by 30. What's 8.10 divided by 30? Zero 0.27, thank you, well done. Okay, what about oxygen? 30.24 divided by 32. 30.24 divided by 32. Yep, 0.945. Carbon dioxide, 23.76 divided by 44. 0.54, excellent, well done. And finally, water, 14.58 divided by 18. Okay, 0.81. All right, so what we can see here is that the decimals don't look that nice, but they will work out. So the smallest one is 0.27. So if we make 0.271, what is 0.945 divided by 0.27? 0.945 divided by 0.27. 3.5, excellent. So someone's asking me how many decimal places should you do it to? So in this case, when we're working out the number of moles, I would write out as many decimal places that are there, and you would always find that it's a nice number. So what you've just seen there is when we did 0.945 divided by 0.27, we got 3.5. So that's a nice number. 0.54 divided by 0.27 is 2. And then what's 0.81 divided by 0.27? Excellent. So someone is saying 3, well done, good. So what we can see here is that we have a decimal. Now you may remember from last week that when we balance equations, I always say we don't like decimal places or we don't like fractions. So in order to balance it, we have to double everything. So that means this becomes 2, so it'd be 2 ethanes. Our oxygens become 7, our carbon dioxides become 4 and our waters become 6. And we can just check that that's balanced. There are 4 carbons on the reactant side, 4 carbons on the product side, 12 hydrogens, 12 hydrogens, 14 oxygens, and if we have a look here, we've got 8 plus 6, which is 14. So that's a fully balanced equation. Well done, everyone. Okay. So now that we've done that, we're moving on to limiting reactants. So the reactant that gets used up first is the limiting reactant, and therefore it's not in excess. So we can work out the limiting reactants if we know the moles that we started with. So just as an example, if we've got 5 dogs that we need to feed, but we've only got food for 4 dogs, the limiting reactant would be the dog food. And that's because we don't have enough dog food. So effectively, that means that we would only have enough food for 4 dogs. So we can only feed 4 dogs. It's the same in a reaction. In a reaction, you would find that you have a mass of both of the reactants, and one of the reactants will be limiting, i.e. one of the reactants there's not enough of to react with the other one, so we have to use the mass of one of them. And I'm going to explain that using a question. First of all, we always only look at the reactants when we're thinking about limiting reagents. It's always reactants, so we can ignore the products. We don't need to know the masses of the products or the moles of the products. We just need to know about the reactants. So here it says there are 10 grams of sucrose. This is sucrose over here. And 10 grams of oxygen. That's oxygen. Which is the limiting reagent? So we'll go through this slowly and see if we can work it out. So there are 2 methods. I'm only going to show one method today, and that's the method that I think is the simplest to understand. So there are 10 grams of sucrose and 10 grams of oxygen. So the method that I like is that we work out the number of moles of one of them, and then we use the reaction or the balanced equation to work out the number of moles of the second one, to then see if the mass is equivalent to that. So to understand that, I'm going to go through this question. So if we have a look at sucrose, there are 10 grams of it. So if we calculate the number of moles of sucrose, we know that the moles equals the mass over the MR. The mass is 10. The MR of sucrose, does anyone know what the MR of sucrose is? So it's 12 times 12, which is 144. Hydrogen is 22 there, and oxygen, it's 16 times 11, which is 176. So what's 144 plus 22 plus 176? Excellent, 342. Okay, so the number of moles of sucrose is 10 divided by 342. So what's 10 divided by 342? That's the number of moles of sucrose. Excellent. So we've got 0.03, 0.029. So try and keep it in its exact form on your calculator. You only ever need to reduce it down to 3 decimal places or 3 significant figures as your final answer. This is not our final answer yet, so we try and keep it as what it says on the calculator. So it's about 0.029. Okay, excellent. So if that's the moles of sucrose reacting, what is the moles of oxygen? Remember how we look at the equation. So if the moles of sucrose reacting are 0.029, what do we need to do to this to get the moles of oxygen? Look at your balanced equation and see if that helps. So times by 12. Excellent. Whoever said times by 12, that's a really good answer. And the reason we times by 12 is because if we look at our equation, there are 12 oxygens there. So that means the ratio of sucrose to oxygen is 1 to 12. So if there are 0.029 moles of sucrose, that means there are 0.029 multiplied by 12 moles of oxygen. So what's 0.029 multiplied by 12? Someone's asking me, where did 10 come from? 10 came from the mass of sucrose. Good, 0.348. Yep, so 0.348 is the moles of oxygen. So the moles of oxygen is 0.348. Remember then to calculate the mass of oxygen, and the reason we're calculating the mass is to see if oxygen is the limiting reaction or not. So 0.348, we multiply then by the AR of oxygen. Oxygen has an AR of 32 because it's O2. So 0.348 times 32, what's that? 0.348 times 32. 11.136. Okay, so what we can see here is that if the number of moles of sucrose is 0.029, we would need 11.136 grams of oxygen to react with that sucrose. But in our question, we only have 10 grams of oxygen. So that means oxygen is the limiting reactant or the limiting reagent. So remember, I'm just going to go through that again. We had 10 grams of sucrose. So we calculated the number of moles of sucrose and we got 0.029. We then used that to calculate the number of moles of oxygen that would be reacting if we had 0.02 moles of sucrose, and that amounted to 0.348. Then we calculated the mass using that, so 0.348 times 32, and we got 11.136. So that means that the oxygen is the limiting reactant because we don't have 11.136 grams of oxygen, we only have 10. So there's less oxygen compared to sucrose. So that means that not all 10 grams of sucrose can react, but all 10 grams of oxygen can react. Any questions about that? Where does 32 come from? 32 is the AR of oxygen. So remember, it's 16 times 2, and that's because it's O2. Any other questions before we do another question on this topic? Someone's asking me, how did you get 12? So the ratio 1 to 12 is because there's 1 sucrose to 12 oxygen. So remember, we look at the big numbers in front of the compounds or elements. So sucrose has no number in front of it. That means there's 1 sucrose reacting with 12 oxygens. So the ratio is 1 to 12. That means if we have 0.029 moles of sucrose reacting, we have 0.029 times 12 moles of oxygen reacting. We don't look at the other side of the reaction because this question is about limiting reactants. Remember, when you're reacting something, it's not about the products you form, it's about the reactants. So you want to know which reactant is limiting. Okay, great questions. So let's do another one then. Aluminium reacts with chlorine gas to form aluminium chloride via the following reaction. Again, we can ignore the aluminium chloride. We want to know whether aluminium or chlorine is the limiting reactant. What is the difference between MR and AR? Excellent question. AR is the relative atomic mass. MR is the relative formula mass. So if we have a look here, AR of aluminium is 27. Aluminium is an element, therefore it has an atomic mass. But the compound, aluminium chloride, would have a relative molecular mass, which is the ARs added up in aluminium chloride. So it would be Al 27 plus 3 times 35.55. So the relative molecular mass is of a molecule or a compound. The atomic mass is just an element or an atom. Okay, so aluminium reacts with chlorine gas to form aluminium chloride by the following reaction. How many grams of aluminium chloride could be produced from 34 grams of aluminium and 39 grams of chlorine gas? So in this question, we do want to know about the aluminium chloride because they've added another step to the question. First of all, we need to work out which is the limiting reactant. And then we need to work out what's the maximum mass of aluminium chloride that can be formed given the limiting reactant. So again, we'll go through it slowly. Let's work out which is the limiting reactant first. So I will start with aluminium. Let's calculate the moles of aluminium. So the number of moles of aluminium will be 34 divided by 27. So what's 34 divided by 27? Remember, it's the mass divided by the AR. 34 divided by 27, what's that? 1.259, excellent. Yep, good, just remember to keep it as what it says on the calculator. So 1.259 moles. Then if we look at our equation, the moles of chlorine are 3 and the ratio is 2 to 3. So to convert this into the number of moles of chlorine, we divide by 2 to get what 1 mole is, and then we times by 3. And that's because the ratio is 2 to 3. So at the moment, this is representative of 2, but we want 3, so we divide by 2 and times by 3. So what's 1.259 divided by 2, divided by 2 and times by 3? So 1.259 divided by 2 multiplied by 3. What's that equal to? Remember, we're using the ratio there, so the ratio is 2 to 3. Great, 1.8885. So the number of moles of chlorine is 1.8885 or 1.885. Excellent, well done. So that means the mass of chlorine, or what we expect if we react all of the aluminium, is 1.8885 multiplied by the AR of chlorine, which is 35.5 times 2, which is 71. So what is 1.8885 times 71? That will give us the grams of chlorine that would react with that aluminium. 134 we've had from someone. Anyone else? 1.8885 times 71. What does that equal? Good, 134.0835. Okay, now let's have a look. What grams of chlorine is in the question? 39. But you told me we need 134 point something grams. So what that means is that chlorine is the limiting reactant. So if chlorine is the limiting reactant, we can only use 39 grams of chlorine. So that means we now need to work out the moles again using chlorine. And the reason for that is because chlorine is the limiting reactant, we're not going to use up all the aluminium chloride. So this many moles are not going to react. In fact, it's the moles of chlorine that are going to react, and that's because chlorine is the limiting reactant. So the number of moles of chlorine will be 39 divided by 71. So what's 39 divided by 71? 0.549. Excellent. So that is the new number of moles. It's 0.549. So 0.549 moles of chlorine react. We want the maximum mass of aluminium chloride. So if 0.549 is equivalent to 3, we want what 2 is. So now the ratio is 3 to 2. So remember, to get what 2 is, we divide by 3 and multiply by 2. So what's 0.549 divided by 3 and multiplied by 2? Someone's asking, is this for the higher tier? Yes. This, you have to be able to calculate limiting reactants in the foundation tier, but this particular question is a higher tier question. Great, 0.366. So the number of moles of aluminium chloride formed is 0.366. Then to calculate the mass of aluminium chloride, we multiply that by the MR. So that is 27 plus 35.5 times 3. So 27 plus 35.5 times 3. So what's the final answer then? What's the mass of aluminium chloride that is formed? So you can calculate what's the MR first. So 27 plus 35.5 times 3. What's the MR of aluminium chloride? And then you can multiply that by 0.366 and you should get a final answer. Great, 48.861. Great, the MR is 133.5, that's exactly correct. So we do 133.5 times 0.366, and that should give you an answer of about 48.862, and then to 3 significant figures, that is 48.9. So the final answer then is 48.9 grams of aluminium chloride. Excellent, well done everyone. Okay, we won't do this third question. We might do it at the end if we get time. Okay. So I'm not sure what's happened to that slide. That's okay. So we're thinking about percentage yield now. The percentage yield is very similar to questions that we've already done. And it essentially says that if we react 2 reactants together, let's say A and B, and we form C, we would expect to form a total amount of C when we react A and B. So if A is 2 and B is 3, we would expect to form 5 grams of C. But in reality, that doesn't happen. Because when we react something, there are lots of different factors there that may affect that percentage yield. So for example, we might not have it at a high enough temperature or a high enough pressure to form 5 grams. So although in theory, we can produce 5 grams, we might only produce 4 grams when we actually do it as an experiment. So the percentage yield is about, well, how much did you produce? 4, over how much is theoretically possible? 5. So 4 over 5. So that's, then we multiply that by 100. So the percentage yield is 80%. 4 over 5 times 100. So the percentage yield equation is the mass that is over the total mass that is theoretically possible. So remember, there is always a theoretical possible answer that we calculate. So all those masses we just calculated of aluminium chloride, for example, that is a theoretical mass or a mass we expect to produce, but it's not necessarily what we will produce when we do the equation, the reaction in a classroom, for example. So let's have a think then how we calculate the theoretical mass and then how we calculate the percentage yield. So for the balanced equation shown below, if the reaction of 20.7 grams of calcium carbonate produces 6.81 grams of calcium oxide, what is the percentage yield? So first of all, we've been told that we're reacting 20.7 grams of calcium carbonate, and we produced 6.81 grams of calcium oxide. Therefore, in this question, we should be able to produce more calcium oxide, but we're not. So we need to work out what the theoretical yield mass is. So we've got the mass produced. So remember, the percentage yield is equal to the mass produced divided by the total theoretical mass, or the total calculated mass. So our mass produced currently is 6.81. But we need to know what that total theoretical mass is, or X. So to calculate that, we need the number of moles of calcium carbonate, and then we can use our reaction to have a look. Let's just check our reaction is balanced, because we don't want to be caught out like that. So if we have a look, there's 1 calcium on the reactant side, 1 calcium on the product side, 3 oxygens, 1 carbon, 1 carbon. So it's a fully balanced equation. That's very important. So now the moles of calcium carbonate, the equation for percentage yield is just here. Percentage yield equals the mass produced over the total theoretical mass. Great. Okay, so the moles produced, the moles of calcium carbonate is 20.7 divided by the MR. So the MR of calcium carbonate will be 40 plus 12, which is 52, plus 3 times 16, which is 100. So well done for everyone that's telling me 100. That is the MR of calcium carbonate. So 20.7 divided by 100. So what's the number of moles then of calcium carbonate? So we don't need a calculator to do that. 0.207. Yeah, excellent. So 0.207. Good, well done. So if that's the number of moles of calcium carbonate, if we look at our equation, it's a 1-to-1 ratio for calcium carbonate to calcium oxide. So that means there are also 0.207 moles of calcium oxide. So then the percentage mass, or the total theoretical mass that could be produced of calcium oxide, is 0.207 times the MR. The MR of calcium oxide is 40 plus 12, so calcium plus carbon, which is 52. So what's 0.207 times 52? 0.207 times 52 to get the great 10.765. Good, so 10.765 is the maximum theoretical mass that could be produced. So what that means is, if we have a look at our question, we only produce 6.81. So the percentage yield is 6.81 divided by 10.765. Remember, it's a percentage, so we multiply by 100. So what is 6.81? That's the maximum mass, or that's the mass we produced, divided by the total theoretical mass, or the mass that we think could be produced, multiplied by 100. That should give you a nice percentage yield. What is the percentage yield? Okay, someone's telling me it's 10.774. That's fine. We'll put it down to 10.774. Great, 63.3. Again, you can do it to 3 significant figures. So yes, it would be 63.3%. So the percentage yield then is 63.3%. Okay, let's do another question then. Okay, so for the balanced equation shown below, if the reaction of 91.3 grams of ethene produces an 81.3% yield, how many grams of carbon dioxide would be produced? Sorry, that's propene. So we've got a balanced equation, and they've told us it's balanced. That's really important. We've got 91.3 grams producing an 81.3% yield. So it's a different type of question where we've been told the yield, and we need to know how many grams of carbon dioxide would be produced, i.e. what's the mass that you produced, and we've been given the percentage yield. So we know that 91.3 grams of propene reacted. So that means the number of moles of propene would be 91.3 divided by the MR. So the MR of propene will be 36, so 12 times 3, 36 plus 6, 42. So what's the number of moles of propene? 91.3 divided by 42, what's the number of moles? So 91.3 divided by 42 will give us the number of moles. Great, so 2.173. Brilliant, well done everyone. So 2.173 moles. That's the moles of propene. We want to know about carbon dioxide. So let's have a look how many moles of carbon dioxide can be produced. If we look at this reaction, the ratio of propene to carbon dioxide is 2 to 6. 2 there, 6 there. So this 2.173 represents 2. We want 6, so we can just multiply by 3. So the number of moles of carbon dioxide will be 2.173 times 3. And that's the number of moles. And then remember, to get the mass, we multiply by the MR. So the MR of carbon dioxide is 12 plus 16 times 2, which is 32 plus 12, which is 44. So if we type that into the calculator, we should get the maximum mass of carbon dioxide that can be produced. So what's the maximum mass of carbon dioxide that can be produced? So 2.173 times 3, and then we multiply that by 44. So what's the maximum mass? So people are saying 6.52. So yep, that's the number of moles of carbon dioxide. What's the mass? Okay, great, 286.836. Excellent. So if we have a look then, they're saying we produce an 81.3% yield. So if the maximum or total theoretical mass is 286.834, to calculate the mass that we produced, we need to then multiply that by the percentage yield. And that's because they told us the percentage yield is 81.3%. So essentially, the mass that we produced in the lab will not be this, it will be 81.3% of this. So remember, to calculate a percentage of something, we times by the multiplier, which in this case is 0.813, because that means that we're producing 81.3%. So what is 81.3% of 286.834? Oh, sorry, someone's telling me it should be 836. So 286.836 times 0.813. Again, what's the percentage then, or the mass that we produce? Oops. Yep, 230.75. Great, so that means that the mass that we've produced is 230. Does everyone agree with that? Great, 230.75. So the grams of carbon dioxide that we actually produced was 230.75 grams. So remember, if, for example, they told us we produced 230 and we needed to calculate the percentage yield, but we know that the total theoretical mass is 286, we would just do 230.75 divided by 286.836 times 100, and you should get 81.3. So this was just working the other way. So we worked out the total theoretical mass, and then we did 81.3% of that. Okay, so let's go on to the Q&A then, before we do any more questions.
Brilliant, I'll just have a look. And guys, if your question hasn't been answered yet, if you could just pop it in the chat again, just because there have been lots of messages today, so it's harder to comb through those. We had one that asked, can you explain what to do after getting Cl is limited?
Yep. So I think you were talking about this question here where chlorine was the limiting reactant. So that's great. So we got that when we reacted aluminium with chlorine, there wasn't enough chlorine. So we did that by calculating the moles of aluminium, and we got that the moles of aluminium was 1.885, sorry, 1.259. We then had a look and what's the moles of chlorine gas. So we used the reaction to help us. And we saw that the number of moles then when we got the chlorine, it was 1.8885. We then calculated the mass of chlorine, and the mass of chlorine came to 134 point something grams. And we essentially said, but we don't have that many grams, we only have 39 grams. So in this question, it's about saying, well, the limiting reactant is the one that we don't have enough of, and we didn't have enough chlorine. So that means that in the reaction, only 39 grams of chlorine reacts. So then when we wanted to work out the total mass of aluminium chloride, we said that there are 39 grams of chlorine reacting, so we need the number of moles of chlorine, and then we used the reaction and said that there's a ratio of 3 to 2 chlorines with aluminium chloride. So then we worked out the number of moles of aluminium chloride to then calculate the mass. Someone's asking, were all the questions for the higher tier? So no, all of this stuff that we've covered today is in both tiers. Some of the questions are a bit harder. So this question that we're just looking at here, this one here, is a higher tier question. The percentage yield questions, most of them are foundation tier as well. And the limiting reactant questions, most of them are foundation tier as well.
Great. And question, if aluminium reacts to chlorine, does chlorine react to aluminium?
I'm not sure what you mean by that question, but essentially, if I think you're asking if does aluminium react to chlorine and therefore does chlorine react with aluminium? Yep, it doesn't matter which order you put the reactants in, they're both going to react with each other. This question specifically is asking, we've got a certain mass of aluminium, we've got a certain mass of chlorine. Just like with the dog food example I gave, if we've got 5 dogs and only 4 dog food portions, that means we can only feed 4 dogs. In this case, we've got 39 grams of chlorine and 34 grams of aluminium. We don't have enough chlorine to match with 34 grams of aluminium. So that means the maximum mass that can be reacted of chlorine is 39 grams. So we don't react all the 34 grams of aluminium. So there'd be some aluminium left over, and that's because chlorine is limiting.
Cool. Should we do a few more questions if you have them, Aman?
Yep, that's absolutely fine. Okay, so I've got another question on masses from equations. So we started with this today. So let's do the first one then. 2 grams of hydrogen reacts with 71 grams of chlorine to make hydrogen chloride. Use this information to construct a balanced equation for the reaction. So 2 grams of hydrogen reacts with 71 grams of chlorine. So let's try and write an equation first. We've got hydrogen reacting with chlorine. Remember, hydrogen always goes around as a pair. It's a gas, so is chlorine. It's a halogen, and that's going to produce hydrogen chloride. Remember, to write the compounds of hydrogen chloride, we need to know their charges. So hydrogen and chlorine always forms HCl, and that's because of the positive and minus charge. So it forms hydrogen chloride. So that is our balanced reaction there. To calculate then the balanced equation for it, so 2 grams of hydrogen reacts with 71 grams of chlorine. Remember, the mass of the reactants equals the mass of the products. So what's the mass of hydrogen chloride formed then? If we've got 2 grams of hydrogen reacting with 71 grams of chlorine, what mass of hydrogen chloride will be formed? Remember that the total mass of the reactants will equal the total mass of the products. So if we've got 71 grams of chlorine, 2 grams of hydrogen, what's the mass of hydrogen chloride formed? Excellent, 73. So this is 2, this is 71, and this is 73. Excellent, well done everyone. So then we need to use that information to construct a balanced equation. So if we work out the moles of each, so the AR of hydrogen is 2, and the reason for that is hydrogen has an AR of 1. There's 2 hydrogens, so it's 2. Chlorine is 35.5 times 2, which is 71, and hydrogen chloride is 1 plus 35.5, which is 36.5. So now let's calculate the moles of each of the reactants and products. So hydrogen will be 2 divided by 2, which is just 1. Chlorine will be 71 divided by 71, which is just 1. Hydrogen chloride will be 73 divided by 36.5, which is 2. So that means in the equation, to balance it, there will be 1 hydrogen reacting with 1 chlorine to produce 2 hydrogen chlorides. We can then check if that's balanced. 2 hydrogens on the reactant side, 2 hydrogens on the product side, 2 chlorines on the reactant side, 2 chlorines on the product side. Hopefully that made sense. Well done, everyone. Okay, let's do another limiting reactants question. So we have a look at this one here. Ammonia reacts with oxygen to produce nitric oxide plus water. In an experiment, 3.25 grams of ammonia reacts with 3.5 grams of oxygen, which is the limiting reactant. So again, remember, we're looking at limiting reactants. We don't look at the products, we're just looking at the reactants. The clue is in the style of question. 3.25 grams of ammonia. So if we look at one of them then, the moles of ammonia will be 3.25 divided by the MR of ammonia. So the MR of ammonia is 14 plus 3. That's because hydrogen is 1, but there's 3 hydrogens, so it's 14 plus 3. So what's 3.25 divided by 17? 3.25 divided by 17. What's the number of moles of ammonia then? Great, so we've got some answers coming in. 0. Okay, so we've got some, yep, so 0.19, great. Well done, everyone. So 0.19117. Okay, so if that's the number of moles of ammonia, that means then if we look at our ratio of ammonia to oxygen, it's 1 to 1. So that means there's that many moles of oxygen reacting as well. So the mass of oxygen will then be the moles times the AR. The AR of oxygen is 32 because there's 2 oxygen, so oxygen goes around as a pair. So it would be 0.19117 times 32. What's that equal to? 0.19117 times 32. 6.1176 approximately. Okay, if we look at our question, we only have 3.5 grams of oxygen. So that means the limiting reactant is oxygen. There's not enough oxygen to react with 3.25 grams of ammonia. Okay, we probably have time to do one more question. So it's up to you. Would you rather do a limiting reaction question or a percentage yield question? What's the preference? You can do another limiting reactant or a percentage yield. Percentage yield? Okay, let's do percentage yield. All right, so for the balanced equation shown below, if the reaction of 0.112 grams of hydrogen produces 0.745 grams of water, what is the percentage yield? So 0.112 grams of hydrogen. First of all then, let's find out the number of moles of hydrogen. So the number of moles of hydrogen will be 0.112 divided by the AR of hydrogen. Remember that is 1 times 2, so it's 2. So what's 0.112 divided by 2? 0.112 divided by 2, what's that equal to? 0.056, excellent, well done. So there's 0.056 moles of hydrogen. If we then look at our reaction, we can see that there's a ratio of 4 hydrogens producing 4 waters. So the ratio is 4 to 4, which is equivalent to 1 to 1. So that means there are also 0.056 moles of water. So we then need to calculate the mass of water. So we do 0.056, we multiply by the MR of water, which is 1 times 2, so it's 2 hydrogens, plus 16, which is 18. So what's 0.056 times 18? So 0.056 times 18, what's that equal to? 1.008, brilliant. So then if we have a look at our question, we can see that we only produced 0.745. So the percentage yield will be 0.745 over 1.008. And then we times by 100. So what's the percentage yield then? So 0.745 divided by 1.008 times 100. Great, 73.9. So remember, to 3 significant figures, 73.9%. Excellent, very well done, everyone. Okay, so there's another question on the screen that you can have a go at in your own time. I don't think we've got time to do it today, but really well done. On Friday, we'll be looking at atom economy and concentration questions.
Brilliant, thanks, Aman. Just one quick question, which was, let's have a look. In these science questions, will you be allowed a calculator?
Yes, you are always allowed a calculator in chemistry GCSE. In all 3 papers.
Brilliant, cool. We'll wrap up there then. Thanks so much, Aman, for today's session. Thanks everyone for being so engaged today. As usual, you'll be able to find this recording as of this afternoon on the My Tutor YouTube channel, so you can recap and access any previous tutorials as well. So if you're joining us for another session today, we have maths coming up, we have biology, we have physics, and if not, then we'll see you in your next GCSE chemistry session. Thanks, guys. Bye.
Bye.